Hi. So today I'm going to talk about salvage logging and some of the things that we've learned about the impacts of salvage logging on erosion and water quality. So I think I'll get started with an actual slideshow, show you where we're at. Okay, you should see my screen now. And a couple of things that I really want to focus on today would be stream-sized buffers, skid trails, and slash treatments that we can use for skid trails to help reduce erosion, and what the bigger impacts are from this salvage operation. So with that, I'm going to move forward. These are the things that I think we've already covered today. What are the benefits of doing salvage? Your revenue. You're trying to get some money back to the forest or to the private land. You're trying to reduce some of that fuel loading for future wildfires. But the concerns are soil productivity, erosion, water quality, and effects on fish habitat. Big concerns. So if we are going to salvage, how can we do it and have less impact? Well, that's what I'm going to try to go through today. So we started this work years ago, back in early 2000s, looking at the impacts of salvage logging. So I'm going to give you a summary of some of our results from 3 different fires. One of them is the 2006 school fire, 2006 Red Eagle fire in Montana, and the 2009 Terrace Mountain fire in British Columbia. And one of the biggest concerns is rill erosion in the post-fire environment. Once the water concentrates and makes a rill, that's what's going to move sediment down the hill and into the stream course. So we have an experiment that we use that's designed to do just that, make rill erosion happen so we can measure it. We can measure the rates. And that's what we're going to be talking about today, of how we do that experiment, but most importantly, what are the results that we learned? So this is a picture of our experiment. We put water down, different flow rates over different distances with different treatments. It might be a skid trail with no treatment, skid trail with some slash on it, might be a fellow buncher trail, and it might be another area where we don't have any logging equipment. Because we've been looking a lot at ground-based equipment and their impacts on salvage, since that's the most common way that we're removing these trees in the post-fire environment. So the equipment, we looked at a forwarder, we looked at tracked skidders, and we looked at wheeled skidders and feller bunchers. Okay, so with all of those different pieces of equipment, guess what? They have a different impact on the ground surface, which will influence the amount of erosion that happens. So let's just look at some of our results from our RILL experiments. On the y-axis is the runoff rate. On the x-axis down here are the different types of skidders: fellow buncher, tracked, wheel, forwarder. And over here we have our different sites: the Red Eagle, the school fire, and the Terrace Mountain. And at the very top we have post-fire year, use a laser pointer, post-fire year 1, post-fire year 2, and post-fire year 3. So this is runoff rate, liters per minute. So 10 liters, so 10 water bottles per minute, 20 water bottles per minute. Think of it that way. As we increase the traffic and the impact of that traffic, guess what? We increase the amount of runoff, no matter how we look at it. So here's our track skidder and our wheeled skidder at the Red Eagle site. At this site, here's the forwarder, here's our control. So you can still see that we have an impact there. And down here, we have a track skidder versus no treatment. And in all cases, we're increasing the runoff, well, because we're doing some compaction, right? So we're compacting the soil with heavy equipment. Guess what? We're reducing the infiltration. If the infiltration is reduced, then we're going to increase that runoff. That kind of makes sense. All right. So now let's look at the sediment flux. That's the amount of soil that we detached. This is in a log scale on the y-axis. Grams per second is the units that we happen to measure it in. The thing to be looking at is that we have an order of magnitude increase when we use equipment out there because of that disturbance. Okay, so here's the fellow buncher, here is the track skidder, and here's the wheeled skidder. Year 1, year 2, year 3. And you see that the wheeled skidder produces more impact, more sediment than the tracked. Well, remember, what happens with that? With a wheel, the pounds per square inch is much greater than it is on a track, because the track spreads out its weight over the whole length of that track. So it kind of makes sense that the wheeled, which compacts the stuff more and often churns things up more as the wheels turn, that we tend to have more sediment that comes off. We had more runoff, and now we have more sediment. Let's look at that Feller buncher that was used, the forwarder that was used on the school fire. You know, the slope of the line is a lot less here. Well, that tells us that the impact of that forwarder is probably less than the impact of some of the other equipment. Then down here is the track skidder at this one site. And we see that, yes, we keep getting an increase in the, with that track activity, even those tracks, we still increase the amount of sediment that we get. So now we'll talk a little bit more about doing things that would help reduce that impact. Okay. Before we do that, let's go over a couple other little details here to add to that story. Bulk density. Here is at the surface, we can see that as we do different types of equipment on the ground, we increase that bulk density. What I talked about is that if we increase the bulk density, we reduce the infiltration, right? Because we compact the soil. Water isn't going in as fast, we get more runoff. Here it is. Here's the data to help support that. And then here it is down deeper, 10 and 15 centimeters. So that bulk density isn't just at the surface, it's down because of the weight of those equipment. All right, we're going to talk about mitigation. But to do that, I need to introduce you to two new fires. One of these is the 215 North Star fire in Washington State on the Colville Indian Reservation. And the other one is the 2016 Cayuse Mountain fire on the Spokane Reservation. Both of these are in Washington State. And these fires presented an opportunity to look at some salvage logging and also look at the time span that salvage often occurs. So what we did in this case is that we had our burn but not logged, so high severity burn without any logging activity. There's the skid trail with no treatment, typical skid trail. And then what we did when the skidder came back up the trail to get its second load, we had the operator grab some slash from the landing, right, from the slash pile at the landing, and pile it on the side of the skid trail when they went back up the hill. When they were all done using that skid trail, that last trip down, we had them spread that slash back onto the skid trail, kind of to provide extra ground cover, right? So with that, we did our RILL experiment, same experiment where I showed you earlier. We now did it here. Here's some of the data. So same experiment that we talked about earlier. My control, so this is high severity burn. There's my skid trail, and there's the treated skid trail with that slash. Sediment flux, 0.7, 1, and 0.3. The letters behind it try to tell you something about statistical significance. Is there significantly more or less sediment with one treatment or the other? The bottom line is that that we see that the skid trail pretty much consistently produced more erosion than anything else. And by putting that treatment on it, hey, guess what? We reduced it. Look over here at the runoff rates. Not a whole lot of difference. 24, 28, 27, not a whole lot of difference, right? A little bit higher on the skid trail and the treated. Same thing here, same thing here, okay? Well, what that tells us that if you compact it and I put slash on it, it's still compacted. So we're still reducing the amount of infiltration we're getting because we compacted it, but we're producing less sediment because of that slash that we added onto the site. Okay. We also looked, another way to look at this is to just look at a larger hill slope, and we compared the annual sediment yield with these sediment fences, these big fences that we collect at the base of it. And we looked at the control, which is high severity burn, no treatment, the skid trail, and then the treated skid trail for 4 years after the fire and after salvage operation. So biggest erosion rates were right after the fire. That first year, there's our treatment, order of magnitude less. Second year, not much difference. We didn't have any storms, didn't produce much of anything. Here's the third year, we had bigger storms. We produced more on the skid trail than we did over there. And then by year 4, these numbers are really small. There's not much going on. So the vegetation recovered. So what do we learn out of this? Adding slash really helps. It's a good thing. Provides cover, helps with that vegetation recovery as well. So if we're trying to reduce the amount of impact we're going to have with a salvage operation and we're using ground-based equipment, the skid trail is the place to put your money if you want to mitigate the impact from an erosion standpoint. So we would recommend that you add slash to that skid trail. So someone's going to ask, well, how much slash should I add? Well, it depends on the size of the material. If I've got 100-hour fuels, so this is the small stuff, 0 to 3 inch, and I add about 4 tons per acre, that's about 60% ground cover. But if I'm doing some of the treetops and it's bigger stuff, 3 to 8 inch diameter, I need about 40 tons to get that 60% ground cover. So for those 1,000-hour fuels, I need more of that by weight to be able to get the same cover amount. Makes sense because it's dense, right? You got a treetop, it's not spread out. So this gives you some guidance as to how much material you need to add to provide 60% ground cover, which is the amount of ground cover that we recommend to really start reducing the amount of sediment that you get. Okay, so ground cover, important. Here's our ground cover after a skid trail, 10%. Here's with the slash, there's my control. And then you can see how they increase over the years. Sediment flux, same graph I showed earlier, okay? Well, how do we map that vegetation recovery? Well, we can do that with some satellite imagery. And we can use some of the indexes that we use in the post-fire environment already. So we use an NVDI, a normalized vegetation index, to create those soil burn severity maps. Well, we can kind of use that same index in a post-fire salvage operation to be able to look at the amount of cover out there after the fire and how that cover amount changes over time. So that's what we did with some satellite imagery. So here's my sediment flux, here's my cover, and also the NDVI. NDVI and cover both vary from 0 to 1, 1 to 80% cover, 0 to 1 NDVI, which is that index. Okay, so this shows you the ground cover, and this shows you the NDVI. So they mirror each other. Okay, so this tells us something that, well, if I have this index that reflects something about the cover, and that cover is related to the sediment, well, then I should be able to relate something about this image that has cover and the amount and the erosion potential that we might have over a large area, like the entire burned unit. So let's look at this. This is worldview imagery. This is about a 1 meter pixel size. And we have some imagery pre-fire, August 2015, immediately post-fire. And then these are the following years to be able to look at that vegetation recovery. Well, they did that salvage operation. So you can see these white things in here. This is the skid trails and road networks that they use to get out the timber in this particular sales unit, because there's no, you can't see any of those in this image right after the fire. We then calculate the NDVI. So the bright image is mostly the green vegetation. The black is when it's more bare soil. And then you can see how the black right after the fire and how it gets brighter and brighter as the years go by. So we get to see the recovery as time goes by. Okay, so here's my ground cover, here's my NDVI values. And so I can see in this image, the year 1, when they started doing the salvage operation, you could see all the skid trails going down to the landings. Okay, and now we can start to see that vegetation recovery in year 2. Okay? Now, with that, we get to come up with that NDVI, and there's that ground cover fraction that we talked about. So by using this index, we can now map with an NDVI value the entire salvage unit to be able to look at that vegetation and that vegetation recovery. So now here's my cover fraction, and then here's my sediment flux, just what I talked about earlier. Okay, so now I can come up with a threshold that if I have an NDVI below 0.3, then I'm going to have an increase in the amount of sediment that I get. And if I have an NDVI above 0.3, more vegetation cover, right? What I show up here, more vegetation cover, and then I'm going to have less sediment. So now I can have a threshold value that I can apply that's going to tie to the amount of erosion that we can expect, because it's tied to the amount of ground cover that we have. Okay. So if I go into this particular cell unit, unit 208156, this is what it looks like. This is the blue outline of that. I just changed the color so I can actually see it. And this is the NDVI value going from 0 to 1. So, right, 0.3 is the yellow in between that we just talked about. So I can pick up that the area of high disturbance is going to be more in the orange color. The area of the green is going to be less disturbance. Okay? So if I zoom into this area right here, this is where we put those silt fences that I just showed you previously. So here's one that is the skid trail, very orange, right? Here's the control, very green, no extra disturbance. There's the green, no extra disturbance. Here's the skid trail that we put the extra slash on. Well, we can actually see a change in that color because of that slash. So we're able to pick that up with the satellite imagery. So now we can start to figure out the erosion potential from the salvage unit or that whole area. Another experiment that we've done is to be able to look at stream buffers, how important and how well the stream buffers really work. So with that, we designed an experiment where we look at the ability of a buffer to drop out sediment in the post-fire environment. So here's a harvest unit. Here's my buffer that just got burned up in a fire, high severity fire, let's say, for an example, or a low severity fire. And if I add the dirty water that we expect to come off of the skid trails down this area that had been harvested, and we add that down into this buffer, is it going to reach the stream? And if so, how much sediment is going to reach that stream? So we designed an experiment to be able to do that. This is what it's like. We add dirty water at a certain rate down the hill, and we measure the sediment concentration as it goes down towards the stream. And by doing that, we get to see how much sediment pops out before it would get to the stream. And we also get to see, does that rill make it all the way to the stream? Like, what is the width that we really need to have this buffer in a burnt environment to keep the sediment out? So we designed this experiment just to be able to answer this question about buffers. Okay, so the first thing we did was just look at the how far does the rill actually travel? Right, we put in different flow rates. So our conversion is down here. So 15 gallons a minute, 25 gallons a minute, 50 gallons a minute. We add, and then we measure how far they go before all the water infiltrates. Here's the unburned. So we also went to an area that was not affected by the fire. This is a high severity 2 months after the fire, high severity 10 months after the fire, and a high severity 22 months after the fire. So as the site recovers, the distance that the water traveled decreased. Makes sense, right? Because we're getting vegetation recovery, slowing things down, allowing more of that water to infiltrate. If I'm on a low burn severity site, 10 months after the fire, I went to about 50, 60 meters. But then after another 22 months after the fire, I'm down to maybe 20 or 30 meters. So we can see that the distance that the sediment, that the rill water actually goes varies depending on how much time it's been since you've done the salvage operation. We'll now look at the sediment. So the idea was, well, how much sediment drops out as I move down that rill? So in the unburned, I dropped out at 1.3 grams per liter per minute. Well, we add about 25 grams per liter in this experiment. 25 grams per liter per minute as it goes down the hill. So doing that math, about 20 meters, we're going to lose all the sediment. Okay, so that's about 50, 60 feet. We're going to drop out the sediment. That's pretty good because that's kind of a well-used standard that you need to have a 50-foot buffer from a green timber sale to keep the sediment out. Well, after a high severity fire, what we found that the sediment didn't actually drop out. 2 months after the fire, when we put that dirty water down, it picked up more sediment as it went down. It didn't drop out anything. It was a plus. Okay. 10 months, we dropped it out at 0.03. 22 months, we dropped it at 0.5. Okay. A low severity fire, 10 months, we dropped it out at 0.7. And then we increased the amount that we drop out 22 months later. So the time and the severity changed how much sediment gets dropped out. So we combine that information and we come up with a table that would give us an idea of how wide the buffers need to be to reduce the amount of sediment getting into that stream. So in a high burn severity site, the first year after the fire, we have to go increase our buffer about 8 times from that 50 foot, so we're 400 feet away. If we wait a year, or in the case of the Forest Service, we kind of bog down in red tape before we can get started, our buffer would reduce to 200 feet. In 2 years, we could be 100 feet away. If I have a buffer that was burnt at low burn severity, initially I might have to be 200 feet away. Year 1, 100 feet. In 2 years, I'm back to a green timber sale buffer as being effective. So now we actually have some BMP guides that apply to that post-fire environment, which is something that we didn't have before. So, summary of what I've talked about today: rill erosion, pretty important in salvage operation. Slash on the skid trail, that's a good thing. Anything to increase that cover, it's a good thing. Buffers are good. You might have to think about variable width. If a buffer has been burned up in the fire, then it's not going to be as effective as it was in a green timber sale, right? That soil burn severity is important to understand its impact on ground cover. The time since fire is also important. Whether you're going to have a case of being able to salvage immediately after the fire, or if you're waiting a year to do that salvage, it will make a difference on the sediment yield. A couple other things that I didn't go over is the disturbance from the salvage equipment does delay that vegetation recovery. We've got some other publications that have come out that talk about that basically we delay that recovery about 1 full growing season when we put equipment on the ground. These publications are available with Tree Search or on our website. Just go to the library button and you can search on my name and you can find all of that stuff. So with that, I think I'll stop sharing and I'll be available to take any questions. Okay, thank you.